Hi folks, welcome to today's episode, Tiny Cameras, Big Insights. I'm here joined now with Ido Molad, Andrei Kovgan, Ruben Felios, and Stav Riga. Folks, thank you so much for taking the time today.
Thank you.
Thank you
Thank
for
you.
having
Thank you
us.
I want to dive a bit deep into some of the things that the company is doing and some of the specific roles that you folks play in doing this. So most failures don't start with a bang. So there's usually a little sign of something happening maybe behind the scenes that people aren't necessarily aware of. There's a tiny visual clue, and that's where you folks operate. But just so I'm clear in how you folks come together, Stav, you build the cameras. Ruben, you install them into helicopters and UAVs,
Yeah,
and you train the algorithms through visual simulations.
exactly.
Simulations, pardon me, not simulations. And Ido, you work with customers to turn this insight into action.
Exactly.
So we all have our roles. And
Yeah.
yes,
And I'm basically the simulating the cases. That's key. We cannot observe by regular camera. So I'm taking 3D environment like you know from cinema or gaming and using these tools to visualize the problem.
okay. It's you guys all are coming together to tackle a big problem. And I want to understand, I'm going to take it, Stav, I'm going to start with you.
Yeah.
Let's start simple.
All right.
So the episode title is Tiny Cameras, Big Problems. Big Insights. Sorry, not big problems. Big Insights. Let's start simple.
Yeah.
What does tiny get you? Not in a marketing sense, not in a, but like actually, what is it?
Yeah. So tiny cameras is the concept of if you want to look something that is very hard to reach or some place where it's really hard to put a normal camera. So we just build cameras that are maybe a few centimeters long. These cameras we can put in a very narrow or small spaces, and then we can look at places that it's really hard to reach by human. So the concept is to just help the technician or the human that is trying to find the problems to observe the areas that it's hard to reach.
And so, what are the area? Like, what are those areas? Just
Yeah.
for the layman that may not.
Okay, so let's for example, just you mean let's say for an elevator, for example, or maybe an engine, or maybe some place inside the plane that is hidden behind something that you need to take off. Maybe you need to take off a few screws to remove a part to look inside. But if you put a very tiny or small camera, then you don't need to remove any parts. You just let the camera do the observation for you. And this really helps a technician. It saves time. It saves a lot of problems that can come from removing such parts.
Some people just call this colonoscopy for machinery. Is you have a tiny camera that you put in the, and you can observe it as a webcam. For example, as you have on a ski pass, you have a camera to watch the snow, or you're surfing and you see the waves on the beach. Same way you can observe some critical parts inside the machinery, like in the elevator strobes, so just to find if there is some issue you need to solve. And you can do it fully remotely. That's what helps you to provide the costs. And,
But it's important to say that it's not that there's a person sitting behind the desk eating a donut and looking at the screen full of the images that we take or the videos that we take. Actually, there's a computer on board the platform where the system resides, and all the cameras are connected actually to this computer, right, Stav? And these computers actually has the trained algorithms that are being trained by the visualizations and simulations created by Andrei, that actually in real time, they monitor the videos and all the streaming that is coming from the cameras, and actually looking for these. For example, if we talk about an engine of an aircraft, it could be an oil leak that is just starting to happen, and we want to detect it when it's still very small before it's becoming too big, or if it's
Or
a
before
crack.
it happens at all, maybe, yeah.
Yeah.
Before it happens at all, it can be hard because you just see the part itself. But when you start by seeing some glimpse or something, some droplets or something like that, then you can detect the leak before it really happens. But something needs to happen so you can see it.
Yeah, well, one of the things we're talking about today is basically how predictive maintenance alongside technology and also human expertise all come together to solve some of these problems.
Exactly. So
And so we're all coming, sorry, you all, I'm humbly guiding you, but you're all coming from different areas. Ruben, I want to stay on you for a sec,
Yeah.
because you install them, right?
I integrate them.
You integrate
yeah,
them.
Yeah.
Talk us through what that process looks like.
Well, that process is like, first of all, understanding what are the hurts and what are the issues that the technicians or the platform itself has. Then I'm taking those use cases. Each area that has a problem or may have a problem, like cracks, leaks, whatever, that's called a use case. And then I can take all of those use cases, take it home, so-called, to the company, and develop along with the team the solution to predict that, to see that, to monitor that, and to teach the algorithm how to visualize that and to see that predict. So after that, I take those cameras or along with the computer and with the algorithm inside of it, and install that together with the owner of the platform, let's say, within the platform. So remove all the parts that needs to be removed, place the camera, place it in the angle, position, whatever it needs to be, focus and adjust all parameters of the camera in terms of light, exposure, and things like that. And then reassemble everything. And now we have a camera that is installed that monitors. All of that data is collected within the computer. So that first step is to learn on real data, on real life method of operation of the system, with all of the aspects of external impacts on the scenery that the camera sees. The camera learns everything. We further mature the algorithms, and then the algorithm can detect and understand itself whether there is a problem or everything works fine.
Thank you. That was extensive. Stav, as someone who builds those cameras,
Yeah.
What are some of the trade-offs that you have to address or tackle or try to avoid?
Yeah. So since you're building a very small cameras, and sometimes you want to observe in a very small distances, you have a lot of trade-off in the area of optics, electrical trade-offs, mechanical engineering. So there is a lot of engineering difficulties in trying to get a good clear image in very small distance, and also try to get a good image with the very same camera in let's say 1 meter. So our cameras, they are built to observe let's say between 20 millimeters to 1 meter. So this is a really big range, and trying to get a good image in this whole range is quite a challenge. Let's say you have to take in considerations that some materials are more reflecting or less reflecting than other materials. You have to take in considerations the vibrations and the light angles and the thermal difficulty, because you want to have a lot of light, but light generates, so you need a power to generate light, and this generates heat. So you need to take in considerations all of these aspects, and still build a very stable camera, because we work in quite harsh conditions as well. So it's a lot of
Well, it sounds to me like you're providing like the vision data as well as just the sensory data.
Yeah.
Right. So, I want to come to you. So when customers say that they're just looking for vibrations or temperatures or some of the things that Stav outlined, what do you tell them when what's your response to that?
So usually the I would say the legacy systems, predictive maintenance systems, or we can say prognostic and health management or condition-based management, condition-based monitoring, they're all monitoring actually scalars, right? It's only one parameter that is being measured, and this parameter is being measured is actually showing an end result, an end effect that sometimes can happen too late, right? Because, for example, if you measure oil pressure, so when the oil pressure goes too low, maybe it's too late already. And if you would have a camera actually managing to or being able to detect that there is a small leak that is just starting, just a small, just like some kind of I would say a sweat of oil coming from a hose starting to happen, we can actually detect that much earlier. That's one aspect. The other thing is that compared to these scalar measurements, in one camera, you can actually measure multiple different scalars, right, with one camera. So, for example, if we take the oil example, we can actually see if there's a leakage in different areas. We can see if there's a hose closure that is starting to actually open. So we can detect that it's starting to open even before the leak is even created. So we provide much more insights. And another thing is that all these measurements, actually all these sensors, they have to be installed on the actual monitored element. And when using a camera, you can actually install it on legacy platforms that haven't been designed to measure these kind of things, and observe the monitored object from afar without having to without impacting on the monitored element at all, and avoiding the need to do a lot of certification efforts and proving that the sensor that you put to measure the new measurement is actually not affecting the monitored element itself.
Wow. And that people are responsive to that. So when they come to you and they say, "What's the why do we need this?" and you tell them the outline, do they see the value in it, or are they a bit more skeptical?
Yeah. So like every new technology, people are skeptical with new technology. They always okay, prove me that what's the value for me, right? With him, what's in it for me?
Right.
So of course, we have to look at eventually what the customer needs. What are the pains? I think Reuven, you mentioned it before. What are the pains that the customers have? What pains we want to solve? And if we talk about that, when you look at the cost of really expensive platforms like helicopters, UAVs, locomotives, they cost a lot when the organization buys them, but they cost a lot more to maintain actually through the whole life cycle. And what we actually come to do is to save a lot of money in this significant cost, the significant life cycle cost of maintenance. And we're doing that by, again, being able to monitor and detect early failure before it happens, that some of the other legacy systems only detect too late. And by that, the customer can actually do more planned maintenance, and he can plan when to replace the part before he needs to replace it. He can actually monitor the condition of the part and perform condition-based maintenance. So, for example, instead of replacing a certain sorry, I'll rephrase.
A certain part or a certain
So
aspect.
instead of replacing, I'm just looking for a specific example. Maybe you guys can help me for certain parts. So if you want to, if there's a certain
road or
certain road that you have to replace, I would say a push-pull road, for example, that you have to replace every once in a while, according to the flight hours. So instead of replacing it when it finishes the flight hours, actually you can monitor the object and decide to do the maintenance procedure only based on the condition that is actually monitored by the camera itself.
Okay.
Instead, for example, if you can see a
Thank you.
crack on an element, and you decide that crack is fine by us yet, but it will be later more problematic. So when the crack will reach a certain size, you will decide to replace the element and not replace it at the beginning of it or at the flight hour that it is designed to be replaced. You can save a lot of money.
Wow. Can we talk a bit about the systems and algorithms that are used for that? So, Andre, I'm going to come to you, if that's okay. So the visual features that the algorithms may pick up, movement patterns, leak signatures, etc. What can you tell me about how those are measured or viewed, or what can you tell me?
Okay, so basically what I'm doing, I'm bringing data set to algo department that developing and measuring training the different kind of algorithms, if it's a classical computer vision or if it's a deep learning. And what I'm providing, basically, the synthetic data, it's called. And synthetic data, what's good with that, that you can build conditions as a clean room or laboratory with the growing, for example, crack. So crack, I build an algorithm that's semi-random, build the crack on different ways, different depth, width, and we can change the conditions, the length of the crack, the propagation of this crack, and also light condition, and make it and separate the different elements of the visionary and as a layers, for example. So I can bring the clean, smooth picture that is fully synthetic. It's unacceptable by the human eye, but it's great for maturing the algorithm. For example, if it has no noise grain like from camera from the high ISO, I can clean it and bring so the developer of the algorithm can focus his development on particular features like how the crack looks without the noise. And after that, we're adding the noise, camera noise, on top of this data set and trying what the difference and how the algorithm reacts. And variation. So basically, I can variate this scenario, different angles, different lenses, cameras, whatever it is. So
Yeah,
it's
and if I can
yeah, sure.
add to your point, so there is a real issue with trying to detect cracks when you in a plane when you never seen a crack in a plane. So this is Andre's real help here is because we want to find cracks in a road that they never seen a crack in it. They saw it break, but they never seen the crack before. So Andre comes here and with the really smart and physical simulations. It's not only just it's a really mathematical simulations, and he creates a real emphasis on a real not emphasis but real simulation of how a crack happens. And this really helps the algo team, and this helps us, and this helps us also show the customer, look, this is what it looked before the break. You never seen this, like, but we simulated it, and we really think this is what it will look like before the part actually breaks. So this is a real help.
It's including the also smoke simulations, liquid simulations. For example, how the drop of oil moves in changing gravity. So, for example, the object moving and the drops goes down, and after that up, and how the algorithm counts. It's like, is it recognize the drop while the drop going up instead of switching the direction in a millisecond? So how it looks like. And we can simulate and try and test different cases.
So it actually speeds up the learning process if we talk about learning algorithms, right?
Yeah. So what does that look like over time, right? So you're building these things, they're recording it, you're speeding up the process. Where does that naturally take us?
It's by request. For example, if we have some case that we need to produce algorithm, something visualize, we define the problem first of all. As for example, product team define the problem and give the input how it looks, maybe some referent images, for example. And on top of that, we starting to build, trying to use the real data, and there's end for real data that can observe and collect. So we are moving to synthetic data when we feed the edge cases, what's called. So even the generative AI can help us in the edge cases, because those are edge cases that no one saw before. Even the deep, even transformers, like huge models, they sometimes cannot generate those cases and simulate them, and also give control on a lower level, for example, to moving some drop on the surface by 1 millimeter, and I want it to act as I want, like to drive it in force fields that I'm able to put in the scene, the force field that's
Andre, let
right.
me take it to a higher customer level language. I would say you ask where does it take us to, right? Eventually, all these simulations bring us to the point that we have a very mature algorithms that actually provides real good performance, meaning that there's a low false alarm rate. Because for like every system, if you bring it to someone and the system generates too much false alarms, the system will be put aside and nobody will use it. So actually the work that Andre is doing is providing our customers relatively at the beginning, when they just deploy the system, and a very efficient system that provides very good probability of detection for a failed element while lowering the false alarms. And that's the important thing when we look from customer point of view, that you get a reliable system they can use from almost day one with relatively small process,
Yeah.
like Ruben described before, of learning or adapting the algorithms that we already have, that we already had the process of learning with these basic algorithms, just training a little bit for the customer, for the specific use case that is being used by the customer, and he gets a very reliable system right away that can really go and either fly with it or work with an elevator, right? That an elevator can work really, really good with it. Or let's say if we take a power turbine that can work flawlessly when there's nobody around, when you can actually consider that whenever there's a problem that the system is monitoring, it will detect it, and it will detect it properly and correctly.
So that's great. I mean, you have the whole life cycle of how it's going. You're right. You don't want to produce a system that creates too many false positives, because then
Exactly.
it's not going to be interesting. People are just going to turn it off.
Yeah.
Or hopefully not turn it off. But they're not going to respond
They'll
well
just
to it.
remove it.
They won't know what the emergency is or what actually
Yeah.
needs attention. So when we go from developing something in a lab to real world adoption, what are some of the challenges there? Because a lab or
Yeah.
a test environment can be easy to can control, but the world is messy.
Yeah.
Yeah.
So how does that look for you?
First of all, the real life is more harsh. The dynamics, the environment that the system sees is always more difficult than we think. For every element, for every product that is out there, and specifically when you talk about the harsh conditions that we place the cameras in, if it's in terms of temperature, if it's in terms of humidity, if it's in terms of vibration and forces that surrounds the cameras or the computer itself even. So you need to do a lot of testing on the hardware itself and on the software that it keeps running, even though the hardware is being attacked, so-called, by nature and by all of the surroundings. So there's a lot of testing, and there's a lot of standards that you go through, and that you put your system within those standards to help.
And then you always meet real life, right?
Yeah.
That, you come and
Yeah.
suddenly
exactly.
you have a light coming from a certain
Yeah.
direction because the
Suddenly
aircraft
there's
is
a
not.
window
Yeah.
that you
There's
didn't
something that I
expect.
didn't
Yeah.
expect. Yeah.
And then we have to actually make a system that can deal actually also with these unexpectancies that can really happen in the field. And I think illumination, as mentioned, as you Stav mentioned
Yeah.
before, is a very, very major aspect of that.
Yeah, and here also Andre really helps me, because in the lab I can do a certain amount of testing with lighting changes and environment changes, but Andre can really simply just generate a whole full data set with lights at various angles, at various luminosity. So it can be very bright, very dark. It can be a red light. So we can just make the life of our algorithm team really hard, because he just challenges them with everything that they might encounter. Also vibrations. I think you can also simulate a few vibrations. So it's things that are quite difficult. It's not impossible, but they are quite difficult to simulate in a lab. And also there is a limited amount of time that you want to invest in a lab in those simulations. But Andre can just do it like that. So
basically, this is a part of also validation of the algorithm, because sometimes we think, okay, this algorithm is ready to develop, and we're starting to test the algorithm by different conditions and find the weak spots of the algorithm, and to rebuild it, or the tune up, or just change it or something, so we can validate it also.
No, because I was going to say, when you were saying you're like testing things in the lab for real world environments, but it's completely, you will never catch up with what the world can offer you.
But you try, you never catch up, but you try to get as much information as you can from the customer a priori.
A priori,
A priori, yeah, that's the word. Okay. So you try to get as much information as you can, and then build the best simulation you can in the lab. So this is something that we did in the last project, and then the installation was really easy. This is really important, the communication, I think, with the customer.
Plus, you can always update your software later on. So when you deploy a system and the system encounters all new conditions that you didn't even dreamed of, that the customer didn't even think about, that can happen. And in cases that the algorithm has some glitches or things like that, rarely happens, but it happens. So you can always learn from that and adjust your algorithm and evolve from that, and then you can use it all across.
And I think that's the nice thing, that from each customer, each new customer that we have, we also learn ourselves, right? We improve our product by every new customer, every new type of platform that we meet, every new use case that the customer challenge us to tackle and find a solution for, and getting to a system that is very flexible, that has a big variety of what we call use cases that it can handle, or algorithms that can actually handle these different use cases and handle them properly, even when meeting a new. But of course, every once in a while, we'll meet something new that will be challenging for us. So it will never end, right? And that's the fun of it, right?
Yeah, for sure. You don't want to, you want it just always out of arm's reach, so you're always growing. What part did the customers play for you in showing you what you need, and versus you showing the customers what they need? What does that relationship look like? Because every customer, I imagine, is different and needs different things.
Yeah. So if you compare, for example, an aircraft with an elevator, right? So the user, if it's a maintenance organization, or the manufacturer or the designer of the aircraft or the elevator, will know the best. What are the points that are either safety critical that we need to monitor, that we provide them value by monitoring, or parts that when they fail, if they don't detect them early, then it will cost a lot of money if they detect them too late. So they know the platform best. They know the places that actually needs to be monitored. And then they challenge us, okay, that's what we need to monitor. Show us what you can do with this element. And then we bring, I would say, the book of the algorithms that we have, right? And we can match the algorithms with each one of these and provide a solution for the customer.
Wow.
Yeah. And I want to also add that the customer usually he tells you that he wants to observe this part, but then we have this challenge to understand how are we gonna put a camera there, right? How are we gonna put the lights there? So we need to communicate with the customer. Let us know where we can be, where we can't be. Like what is a part that is safe for us to put a camera there? So there is a lot of communication going on.
But there has been cases, I think, that customer comes to us and say, okay, I need to monitor, for example, if this nut is starting to open, and starting to talk to the customer, actually find that there is a better way to detect that, right? That there's something else that we can measure that will actually provide better visibility. I think, Stav, you want to give an example of what can give, for example, if we talk about a nut, not just measuring or if the nut is rotating, but actually measuring the number of threads, threads on the screw itself.
Yeah, maybe you can count the threads. Maybe you can count not the rotation angle, but the distance of the nut from the.
It's things that they don't even know they can check, right? That's the whole
idea.
That's the whole idea. They don't even know what the quantities are.
They talk about what hurts them. But,
They come with their existing maintenance procedures, right? And the existing maintenance procedure says, verify that the nut is in place.
Yeah.
Okay, but you can actually measure it on different ways, as we just described.
And also, sometimes we go to a customer. For example, we were at a customer that they wanted to monitor some element in their production site, and they wanted to see cracks. But then they saw the image. They were surprised that the image is good. They said, maybe you can also measure the length of this object that we create, because maybe we can also use your system to replace the mechanical checking that we do manually. So sometimes they just see the image and it opens up their mind and their thinking of the
Yeah, I think it's very
of
much
this
relates
area.
to what James said before, that that it's a new technology, right?
Yeah.
And sometimes the customer, when they come to us, when they approach to us, they think, oh, it's a neat technology, show us what you've got, and they come with an idea. And actually, it takes time to realize, to actually grasp what this technology can do, and it can do a lot, right?
Yeah.
You can do a lot.
And people are receptive, and customers are receptive to that, because maybe they don't always, they're scared of being replaced by AI, or maybe they don't think they even need assistance or any help. So
This is one of, well, those challenges, sometimes mine, but mostly those challenges, to explain where the system does not replace per se the personnel, where it does not replace the personnel, but it can help them. It can help them be more efficient. It can help them be more precise, and make their life easier.
So
I don't know. People like easy life.
And
So
we
you're
actually
telling me.
help. We if you talk about the user, are different users. It's going to be, if we talk about aircraft, it can be the pilot, it can be the technician,
Yeah.
it can be different types of users. It can be the headquarter. Each one has different requirements or different needs. And when we talk about the maintenance technician, for example, that can have the fear of, okay, now the AI is going to replace me. Very fast he realizes that actually the system really helps him, because if you think about a technician that is very tired and has to do a pre-flight check for an aircraft right before the flight, but it's 2 a.m. because there's a very important mission coming up, and he's too tired, and instead of having to crawl into a very small space inside the aircraft with a flashlight, with a torch, trying to find if there's a crack somewhere, he just needs to open the laptop, press run for our system to run the tests that are being run automatically, and it gets the answers pass, and it saves the technician a lot of time. And it can also save the technician the chance of being mistaken, right? Because usually we see that it takes time to mature systems, but once you mature them, they are much more reliable than human. But the technician still needs to look at the results, see that pass, still needs to do some inspections, but it shortens the time that the technician needs to do these inspections, so it's actually helping him.
So this technology is not taking away the decision making of the human. It's just making the boring things much faster in
Exactly.
cost less. So
like it.
in the end, the human is decide to take a flight or not.
The goal is never to remove the human.
No.
Exactly.
Yeah.
It's
You-
just simple your life.
But you
make
can
it easier.
you also you give him a prediction. So you say, I think this area is a pass, or I think there is a defect there, and there is an image showing where is the defect, and then the technician, he just opens the image, he sees, yeah.
And we're providing data, and that's the important thing, because if we talk about the stakeholders again, there's a critical failure, and there needs to be a decision what to do with this failure.
Yeah.
And there's again the technician and the headquarter and the somebody else in the organization, like a pilot, and we need to take a decision. Now, instead of basing that on what the technician describes orally that he saw, you can actually see the recording of the system, because the system also records when there's a failure, and you can download the data, and you can take the data. All stakeholders can come together, look at the data, and take decisions that are based on data and not just by impression of a technician at 2 a.m.
It's so going ahead from where we are now. You folks are known in the aviation, like, to be dealing with the aviation space. Are there any other industries that would benefit from this kind of technology? I mean, I'm sure there are hundreds.
Of
So
course, hundreds. So like we said earlier, so you have the elevators, you have the
Right.
locomotives. Any big machinery that has any types of parts within it that can fail, we can be there.
Let's try to
monitor that.
define the criteria. Like, I think we can say, we already mentioned that if there's a safety critical element that needs to be monitored, we can provide a lot of value there, right?
Yeah.
If the cost of a breakdown time of a platform is very expensive and we can lower this cost, that's another criteria where we would bring a lot of value. What else, guys?
So we mentioned the elevators before. This is one thing that is completely not related to aviation, but this can really save a lot of time. If an elevator stops working, and then you need to call the technician, and this is something that you can really do. And all this industrial area is also
The 4.0.
So
right?
that's another
industrial
criteria.
4.0. Yeah, this is a region where we are starting to
Evolve
get
into.
into. Yeah,
So if there's a big distribution, it's a big amount of these machines that is
Yeah.
distributed in the field that requires a technician. I think
yeah. I mentioned
that's a
the
great
production
example.
site also. A production site that if there is like a chain that is breaking, then it takes you maybe 1 week of downtime of a machine.
But let's take the elevators where we
Yeah.
do cable monitoring, right?
Yeah.
The ropes monitoring
From
of an
aviation,
elevator.
from aviation to elevation.
Yes.
Yeah.
That could be the next
Yeah.
episode's title.
Yeah.
It also can be for like wind turbine, like for green energy. You have those turbines like dropped out of the city somewhere in the forest, and you just remotely can connect to the camera and see instead of sending the someone that you need to crawl up to the turbine and to
Yeah.
see the condition of the
So we can say
Basically
how to
everything.
reach areas, right?
Yeah,
So I think we can say the criteria. If it's hard to reach area or element or a machine, if there's a safety critical element there that should be monitored in real time and provide alerts.
By the way, hard
or
to
let's
reach
just
can
say
also,
the criteria. I would
Yeah.
say it. So now I lost my
Sorry.
harsh
thought. So
conditions because
yeah.
camera can operate in plus 50 and minus 50, so it's
Right.
and not losing the focus distance that happens more in most of the cameras, so camera can track the stay the same in different conditions. That's a critical point here also.
Yeah,
Wow.
and also hard to reach places can also be places that you don't usually send a technician to. Maybe it's really far away from the site that the technicians are working. Maybe it's it can be just a place that you can just put a camera and there is no person there, and it sends the data with the computer to the cloud, and then people can sit in their office and just observe their system that is very far away.
Sounds like it's going to be an amazing thing for out of space. I don't know. That's where my imagination went, where you're building on the moon and we can see all these things far away.
So we do
Next
have experience actually putting cameras on space, but that's for a different
That is
episode
a
maybe.
whole different. That's for a different
Yeah.
podcast universe
Yeah.
that we're going to
That-
build from this episode.
Yeah.
We are running out of time, I'm afraid. I do see that the clock time's arrow moves on always. So I want to close with a quick lightning round. I have a question now for each of you. I want you to answer as quickly and as shortly as possible.
Huh, okay.
So, Ruben, what's the most surprising thing you've seen a Tiny Camera reveal?
I think size of cracks. Yeah, you can see very small cracks in very hard to reach places, and you don't need to disassemble half of your machinery just to reach those roads or.
Short, Ruben, short.
It's okay. It's cutting out of your answer.
Yeah,
No, I'm
Yeah.
kidding. Thank you. Stav, what's the
Yeah.
hardest engineering constraint?
I think vibrations and lighting conditions. I think the glare, like if you're putting a LED light very close to a material, it can just shine very brightly, and you need to figure out what to do with it.
Andre, what's the most misunderstood thing about visual AI monitoring?
Misunderstood that it's you cannot rely on this because we're using the formulas that we predict the weather with them, okay, and we are using render engines that's physically based, so it's actually tracking the light in different bounces, so it's very major. Even if it's synthetic, it's physically based engines and tools. So most of the people think that it's a cartoon. It's not a cartoon. The simulation is built like we're using the same
Full
formulas.
mathematical and physical equations. there.
Exactly. So when someone testing the aerodynamics of the plane, we're using the same tools, almost the same, like adapter for sure, but it's the same as you fly on the plane. Same way we can simulate these conditions.
That is comforting to know. Thank you. Ido, last question of the episode. What's the biggest decision impact you've seen with a customer?
Well, one specific example, a customer had our system installed on the aircraft. The aircraft was about to take off, and there was a fear that there's a problem that should actually prevent the aircraft from taking off. And actually, on this specific flight, it was a test flight. Our system was supposed to be off. So they turned on the system. They saw what is the status of the specific component that they had fear that it's not functioning properly, and they took a decision to take off based on what they saw from our system.
Wow.
Yeah.
Guys, we're approaching the end of the time, I'm afraid. I could talk much longer
Yeah.
about all of these things. It's been super interesting. But one of the main insights I've gleaned today is just how these powerful small cameras can really help people and enterprises see the things that can't be seen and help prevent major problems down the road. So
Yeah.
thank you all for taking the time today. It's been super
Thank you.
interesting.
Thank you,
Thank you.
James.
Thank you for having
Thank
us.
you.